Hello everyone and welcome to the first video on this channel. Today I will be solving the most recent Jane Street puzzle. If you're not familiar with Jane Street, they are basically a tech company that specializes in trading. But the real reason why we are here is because of their monthly puzzles. Usually they have logic, math, game theory, sometimes even some general knowledge puzzles, but they can also be a mix of multiple. They are usually very fun to solve and not so easy, so I decided to give it a try. And I didn't want to publish this video before they posted the solution, because they have a list where you can put your name if you submitted a correct answer, so I didn't want people to just copy the answer from the video and submit it. But now they made a new puzzle for the current month of August, so we can solve the one from last month. Let's get to it. We have an 8x8 board divided into 13 regions. 12 pentaminos, or areas with 5 squares, and 1 tetramino, or a 4-square area. Then to each area we need to add a tower of height 1. So if we imagine all squares being flat and on the same level, then in each area should be one square that is one level higher than the other squares. So in this case, red circle represented the towers. We place a knight on the board. The knight can make classic chess L-shaped moves, but also looking in 3 dimensions. This basically means if knight moves between squares on the same level, it moves in a L-shaped pattern, and if it moves between squares on a different level, it will move in a straight line, because of the 1 square difference in the height. We place the knight in the bottom left corner with score of 0. On the end move, the score increases by n if it stays on the same level. If it moves up a level, current score is multiplied by n, and if it moves down a level, the score gets divided by n, but this move is only possible if score is evenly divisible by n. Knight can visit each square only once, and when it moves, it can pass through towers. In the grid are already written scores after every third move up until move 18. After that, scores are written every k moves, where k is a number larger than 3. Knight stops after it reaches the final tower. The goal is to reconstruct the knight's path. So, after we reconstruct the path, the final answer we need to provide is the sum of move scores of orthogonally adjacent squares to the squares knight did not visit on its path. So, where do we even start? In a normal 8x8 grid, there are many different paths a knight can take to visit every square. What makes this puzzle possible to solve is the rule that each highlighted area must contain exactly one tower. That rule narrows all of those paths to just one singular solution. But we don't know where the towers are yet. The only thing we currently have are the move scores already written in the grid. The problem is that we don't know which score belongs to which move number. But what we do know is that one of the scores must correspond to the third move, and that we start with a score of 0. There are 3 possible operators a move can have. So we can go through all possible combinations and try to match the final scores to the scores in the grid. Since there are 3 moves and 3 different operators, total number of combinations is equal to 3 to the power of 3, which is 27. So I don't have to go through all combinations manually and calculate scores for each move. I created this Python script which does it for me. It takes the number of the current move, list of the move scores with the operator, and number of moves k. It goes through each possible operator and calculates the score for it. Then it recursively calls the function with the new score added. When it reaches the number of moves k, it displays the scores for that combination of operators. Just one thing to note here, it skips the combinations where the division operator wouldn't return a whole number as stated in one of the rules. And that gives us this list of possible combinations. If we compare scores for third moves and values in the grid, we find one matching value of 1 on the G3 square. We can mark the G3 square with the move number of 3. If we look at the moves, we can see that last move had division operator, which means knight went down a level. Since there was no multiplication operator before, we now know that all previous squares knight was on were towers. Moves where knight goes to a tower will be most important in determining the path knight will take. Reason for that is that each area can have only one tower, And moving to a tower means we can disregard all areas that had their tower square already visited. Let's take first 3 moves as an example. Let's take a look at the tower's grid. We can mark the start square as a tower and other squares in that area as regular squares. Now if we take a look at where can the knight go next, and then take into the account it has to move to another tower because of the addition operator, so it stays on the same level, the only available square is c2. We can also mark the squares in that area as well. Next move is to another tower, and if we also consider that the third move goes to g3 square, the only square that can reach g3 on the next move is e3, since the next move has the division operator and it goes down a level. We can also fill out towers in the area with e3 square. For the g3 square, we only know that it's not a tower. As you can see, we managed to find squares for each move using information from tower's grid. But for now, let's stick to finding the operators for all the moves before we start determining their squares. Let's now go ahead and try matching scores all the way up to move 18. On the move 6, there's a match with a score of 16. Then on move 9, with a score of 23. On move 12, it's 528. On move 15, a score of 37. And on move 18, a score of 88. This is the point where scores stop being written every 3 moves and start being written every k moves. And we all know k must be larger than 3. If we look at the scores grid, there are 5 score values that we didn't yet find the moves for. We are currently on move 18, so at most there can be 46 moves until knight visits each square. This means we can limit biggest value k can have to 9. Now let's run the script with k value of 9. From a list of combinations, we can try to search for one of the remaining scores. And it doesn't have to be necessarily on the 9th move, it can also appear on the moves before. When we search for a value of 138, we find a few combinations that have it on move 7. This means k is equal to 7, so rest of the scores are written down on every 7th move. There was also a hint for this in the puzzle's name. Now that we know k, let's find the rest of the moves operators. Even though there's more combinations for 7 moves now, there is still only one matching score, and for move 32, it's 272. For move 39, it's 449. For 46, it's score of 750, and for move 53, it's 1100. This is the current states of the grids after we find all of the operators. This, however, doesn't mean move 53 is the last move. Only that there were less than 7 moves after it, so no new score was written down. This depends on when the knight reaches the last tower, and we don't know which squares have the towers yet. Now that we have a list of operators for each move, we can make a function that searches for all possible paths based on these operators. This will save us from manually going through all options for each move. It also keeps the list of visited squares and list of towers, which are being updated as it goes through each move on a certain path. I also added the list of already known move numbers, in order to shorten the time it takes to go through all paths. The function takes final square it needs to reach, so it knows when to stop. Empty list, where it will keep the moves it goes through, so it can display them in the end. Then a list of already determined moves, visited matrix, operators list, current move, which is the start square, towers matrix, flag if last current move is a tower, and the move number. Function first updates the towers matrix, which starts with all square as unknown, and it then marks the current move, whether it's a tower or not, alongside other squares in the same area if the move was a tower. Then it checks if the next move is already known and the next operator, based on which it also determines if the next move is a tower or not. Now it goes through all possible move patterns, which checks if the next move is legal to make and if it was already visited, and matches the level based on the operator. If all checks were passed, it makes the recursive call with the next move. After the end square was reached on the last move in the list, it displays it as a possible path. Let's run the function. We can see there are still a handful of possible paths. This confirms that knight did not go through all tower squares and that we still need to find last few moves. Because there aren't that many options left, we can search them by hand. For each path, we'll display its visited matrix to see where can the knight move next, and also towers matrix to see which areas are missing the towers. Let's take a look at the first path's tower matrix. It seems only upper right area is missing the tower square, and on the last move 53, knight reached h8 square, which is inside that area. Now, if we look at the visited matrix, there is no square a knight can move to from h8 square, so we know this path is not our solution. This means that we need to search for a path that has a square a knight can move to from h8. Those could be one of the squares f7 or g6 if it's not a tower, and f8 or h6 if it is a tower, and in which case we would find the last tower square. Going through all the paths, and finally on the one before last we find a path where g6 square was not yet visited. We can check the last path too just to confirm, but that is the only path that works and visits all the towers. Now that we have our path, let's fill out the grids and find the final answer. And I forgot to mention this before in the video, but I'll leave a link in the description to a GitHub repository where you will be able to find the code I used in this video, so you can try it out for yourself. Also, feel free to leave any questions in the comments if I didn't explain something. This is taking a little longer than expected. So, what did you have for lunch today? I had some tamagoyaki with rice. I was also thinking about going to Japan. So, when we filled out all the move scores, we sum all orthogonally adjacent squares of all unvisited squares. Those scores sum up to a value of 33,609. And there we have it. That's our final answer. Thank you so much for watching this video. Hope you enjoyed it, and see you in the next one.